Hi guys, today we are going to talk about the YouTube manometer. Let's have a recap of some of the concepts that we learned in our previous lessons. Pressure is equals to force over area. And from this formula, we can have a unit for pressure where force will give us Newton and area will give us meter squared. Therefore, one of the unit is Newton per square meter. Since 1 Newton per square meter is equals to 1 Pascal, we can also use this one as a unit for pressure. Another formula for pressure is H rho G. And from this formula, we can use the two SI units as an SI unit. 1 Newton per square meter and the Pascal. We also have other units for pressure, and these ones are centimeter Hg and millimeter Hg. We only use these units if we know density and gravity, and we also use the liquid where the liquid is specifically mercury. Also, let's remember that pressure, when the pressure is 100 centimeter Hg, it's equivalent to the same thing as 1000 millimeter Hg. And this is because 10 millimeters is equals to 1 centimeters. These are the 3 steps that we can use to solve problems under the YouTube manometer. Step number 1, identify a common height. Number 2, write an equation. Number 3, solve the problem. Look at some of the examples where these steps are applied. So for this particular example, just write an equation for the following YouTube manometer. We will identify a common height. We'll say this is our common height. 2 liquids. But don't worry, we'll go through as many examples as possible for you to understand how the 3 steps are used. To identify a common height, we'll have a height where we have A and we have point B. So at this point, we have, because same height means same pressure, so we'll say same height equals pressure. And remember, it is height above the ground. Height above the ground. Because they are of the same height from the ground, therefore they have the same pressure. Let's say the equation number 2, write an equation. Pressure at point A, let's call it P of A subscript. Pressure at point B is P of B subscript. Because same height means same pressure, say that these two are equal. Let's move to another example. Let's try to solve this problem. Assume that this is mercury. Say we first identify a common height. We want to calculate the pressure of the gas. The common height, it will be a height where on top of it, the gas must be present. For example, if we choose this to be our common height, from here going on to this direction, it can't be our common height because at this position we don't have the gas, and that's what we want to calculate the pressure of the gas. Can't also use, but you can use this one because at this particular level we have the gas above. So we'll say pressure of the gas, pressure at point A, call this region A, and this one region B. So this is the point A, this is the point B. So at point A, only the gas is acting on it. At point B, we have 2 things. This column of mercury and atmospheric pressure because it's open to the atmosphere, P of atmosphere. So we'll say pressure of the gas, say pressure at point A must be equal to pressure at point B because it's same height. But we said that it's same height from the ground. So from here to the ground is the same thing from here to the ground. So because it's the same height, and this point, they are the same height from the ground, and therefore they must have the same pressure. So pressure at point A, that is everything on top of A that is pressing it. That is only the gas. Pressure at point B, that is everything on top of B, this point that is pressing it. So you have two things. We have this column of mercury, and we also have the atmosphere. So we'll say pressure due to the column of mercury, which is H rho G, is for mercury plus, or the liquid that is used, sometimes they can change the liquid, plus pressure of the atmosphere, P of atmosphere. Now, because these two are equal, and this one are equal, because remember it's same height, we will conclude that pressure of the gas, which represents PA, must be equal to pressure PB, which is the whole of this. So the whole of this must be equal to the whole of that. So it must be equal to H rho G plus pressure of atmosphere. And that's how we determine the equation that we will use to solve the problem. So from here, it's much easier because you just key in the values. Let's look at another example. So for this particular problem, we're going to first identify a common height. Because we need pressure of the gas, of this particular gas, we are going to identify a common height, and that height, we say that the gas must be above it. The gas that we want must be above it. So if we choose this one to be our common height, it will bring a problem. It's true the gas is above it, but there's another problem. It will introduce an atmosphere here, something that we cannot calculate easily. We cannot calculate this height or the density of the atmosphere. We have the height here. So this height is the same as this one, but the density of air is not given. So we will just say that we cannot use this particular height, but we can use a different one. It will give us the desired results. This is the one. So for this one, the atmospheric pressure is given. We only need this particular height and pressure of the gas. So pressure at point A is point A, and pressure at point B, this is point B. They must be equal. So pressure at A is equals to pressure at B, and we say that this is because same height from the ground. Height from the ground. Pressure at A is due to two things. So A is being pressed by two things, H rho G and pressure of the gas. So we just say H rho G plus pressure of the gas. Pressure at B is being pressed by two things, pressure of the atmosphere, because it's open to the atmosphere. Now, these two must be equal, this one and this one, they must be equal. So we'll say the whole of this is equal to the whole of this because this one are equal. So we'll say pressure H rho G plus pressure of the gas must be equal to pressure of the atmosphere. And therefore, pressure of the gas, we take H rho G to the other side, we'll say it's pressure of the atmosphere minus H rho G. And that is the final results. Let us look at examples as tested in exams. The first one, the figure below shows a gas trapped in a U-tube manometer. Calculate the pressure of the trapped gas. Take G is equals to 10 newtons per kg. Pressure of the atmosphere is 760 millimeter G, and density of mercury is that. So we have an atmosphere at this point, and pressure of the atmosphere, it's this one. So this is the pressure of the atmosphere, P atmosphere. So you can use P of A or just P or P atmosphere. So we'll use the three simple steps. So the first one, you must identify a common height. For example, in ours, the common height is this one. And in the common height, we have the gas above. And this is the gas. This is what we want. So we'll say at this particular level, say this is A, and this one, it's B. So pressure at A must be equal to pressure at level B. Remember, this one, A, it's inside the liquid, B, it's actually on top of the meniscus. And they are equal because we said it's same height above a level ground. So pressure at A, so at A, it's being pressed by two things. First of all is H rho G due to this column of mercury. Then the next one is pressure of the gas. It's also pressing region A. So we'll say pressure at A is due to H rho G, then pressure of the gas. Then at B, pressure at B is due to two things. It's actually due to only one thing, that is pressure of the atmosphere. So at B here is being pressed by only the atmosphere. So these two, they must be equal. These two must be equal because from this particular point, they are equal. So you'll say the whole of this is equals to the whole of that. So you'll say H rho G plus pressure of the gas is equals to pressure of the atmosphere. So we write the whole equation in terms of pressure of the gas. You take pressure of the gas, or you just take H rho G to the other side. The whole of that H rho G, you take it to the other side, so that you can have pressure of the gas is equals to pressure of the atmosphere. Then you subtract H rho G. So you'll say pressure of the gas is equals to pressure of the atmosphere. We just key in the values, where the pressure of the atmosphere is 760 millimeter Hg, but you have to convert this one to pascals. 760 millimeter Hg, that's a height. We'll say 760 millimeters, we divide by 10,000 to have height in meters. Then we multiply by density of mercury, 13,600. Then you multiply by 10. And the whole of that, this is pressure of the atmosphere. You also you subtract the second part, which is H rho G, pressure due to this particular column of mercury. So we subtract another big bracket, say 50 centimeters. You divide by 100, convert that to meters. You multiply by the density of mercury, because at this particular point, this is mercury, the liquid. Then you multiply by 10. You key in the whole of this into the calculator, and you have pressure of the gas as, the answer is 35,360 pascals. Let's move to the next example. The diagram below shows a mercury manometer. Some dry gas is present in the closed space in limb A, while limb B is open. If the atmospheric pressure P of atmosphere is 100,000 and height is 20 millimeters and the density of mercury is 13,600 kgs per cubic meter, determine pressure of the gas Pg of the gas in millimeter Hg. So we'll say, first of all, we identify a common height. Our common height is this one. In our common height, number one, we have the dry gas on top of it. So we'll say pressure in B, that is here, it must be equal to pressure at region A, that is here. Now pressure in region B, it's being pressed by the atmosphere alone, P of atmosphere. So we'll say pressure at B is equals to pressure of the atmosphere, while pressure in A is being pressed by two things, the dry gas and H rho G, due to that height. So just say pressure of the gas plus H rho G. Now these two are equal, this one and this one. So we'll say if we combine them, because they are equal due to same height, same pressure, we'll say in B is pressure of the atmosphere. It must be equal to the whole of this is equals to the whole of this is equals to pressure of the gas plus H rho G. Let us key in the values into our equation. So we can first start writing this whole equation in terms of pressure of the gas because that's what we want. So we'll just take H rho G, this one, to the other side. So we'll have pressure of the atmosphere is equals pressure of the atmosphere plus pressure of the atmosphere minus H rho G must be equal to pressure of the gas. So let's say pressure of the gas must be equal to pressure of the atmosphere minus H rho G. That's because we took this one to the other side. So we'll say pressure of the gas, then we just key in the values. Pressure of the atmosphere is this one, 100,000 minus H rho G. In this particular case, H rho G, the height is given as 20 millimeters. So we'll say the height is 20 millimeters. That is 20 over 1,000. We are converting the millimeters to meters. Then we multiply by the density of mercury, 13,600. Then we multiply by 10. So you key in the whole of that into the calculator, and your answer will be, the answer is 97,280 pascals. But remember, our answer was supposed to be in millimeter Hg. So just equate the whole thing so that we can calculate the height in meters, then convert it to millimeter Hg. We will say pressure of the gas is equals to H rho G. Whatever we are looking for is this particular height. So we'll say 97,280 is equals to the height that we are looking for times density of mercury, 13,600 times 10. So we'll say the height H is given by, the height H is equal to 0.71529 meters. When you multiply that by 1,000, because 1 meter is equals to 1,000 millimeters, we'll say the height H, which represents the pressure, we'll say that the pressure is equal to this one times 1,000, which is 715.29 millimeter. But because the dense it's Hg, we'll say it is millimeters. Let's move to another example. This one, question 3. The figure below shows a U-tube manometer connected to a gas pump. If the pressure of the gas is 150,000 pascals and the pressure of the atmosphere is 100,000 pascals, calculate the height H. So first of all, we identify a common height, and our common height is this one. This is our common height. So in our common height, we have what we want, which is the gas. We have, in our common height, we have what we want above it, which is the height. Then the gas is also on top of it. So we'll say this is region A, this is region B. So as usual, you just say pressure at A is equals to pressure at B. Pressure at A is due to the gas which is pressing it. That is pressure of the gas. Pressure at B is due to the atmosphere and H rho G, these two. So it's say pressure of the atmosphere plus H rho G. So we'll just key in the values from this point onwards. So pressure of the gas is given as 150,000 must be equal to pressure of the atmosphere, which is 100,000, plus H rho G, where H rho G is height, which we are looking for, times the density of mercury. This is mercury, 13,600 times 10. So the density of mercury will be given in an exam. So you can key in the whole of this into the calculator, or you can simplify it further. by taking this one to the other side. When you subtract 150,000 and 100,000, the answer is 50,000. That should give us H times 13,600 times 10. You divide both sides by 13,600 and you also divide both sides by 10. And there we have H is equals to 0.3676 meters. You can convert this to any other unit, to centimeters and millimeters. Let's look at another example. Question 4. The U-tube shown below contains mercury of density 13,600 kgs per cubic meter and is connected to a laboratory gas supply. If the atmospheric pressure is 75 centimeter Hg, what is the pressure of the gas in centimeter Hg and pascals? So we'll first start by solving Roman 1. For Roman 1, we want the pressure of the gas in centimeter Hg. Now we first identify a common height. The common height is this one. This is the height where we have what we want above it. Then on the other side, above it is everything that we can have in order to solve this one. So in my previous examples, we didn't choose this one to be our common height because of the reasons that I stated. So we are going to say this is region A and this one is region B. So in pressure above it, pressure in region A must be equal to region B. So in region A is being pressed by the gas, so that is pressure of the gas. In region B, at this point, is being pressed by two things: the column of mercury H rho g plus pressure of the atmosphere. So we'll say H rho g plus pressure of the atmosphere. Now, we can reduce the working by calculating pressure in terms of height. Remember, pressure can also be in millimeter Hg or centimeter Hg. So just say pressure of the gas is equals to pressure due to this column, the 75 centimeters. So instead of calculating H times rho times G, we just simplify it by saying that is 75 centimeter Hg. And remember, the liquid is already mercury, so we don't have to multiply everything here. So automatically this represents pressure, but you can convert it to pascals by multiplying by the density of mercury and multiplying it by gravity. Then we add pressure of the atmosphere. Now the pressure of the atmosphere here, it was given as 75 centimeter Hg. So we are also going to add another 75 centimeters Hg. So remember, the first one represents this, that is the column of mercury, but the second one represents the atmosphere. Therefore, the pressure of the gas is equals to the sum of this one and this one, which gives us 150 centimeters Hg. So that is the answer for Roman 1. Now for Roman 2, we will say the final answer in pascals. So pressure of the gas, if you already have pressure of the gas in millimeters Hg, you can convert it to pascals by saying pressure is H rho g, pressure of the gas is equals to H. Remember, this is actually a form of height. So that is 150 centimeters. When you divide by 100, it gives you 150 over 100, and the whole of this is in meters, times the density of mercury, which is 13,600, times gravity, which is 10. So pressure of the gas is equals to, when you key in the whole of this into the calculator, it will give you 20,400 pascals. Let's move to another example. Question 5. The figure below shows a tube filled with water, mercury, and another liquid. A. Determine the density of the liquid. Take density of water is that. And B. State a possible reason why mercury is used. So we'll start first study the whole diagram. So we have a height of the liquid here. Height H of liquid is 22 centimeters. We also have height of water, which is 25 centimeters. We need to choose a common height for us to solve problem A. A common height, I'm choosing this one because when we choose here, we are not going to have the liquid above this particular point. But what we want is a liquid to be above the common height, or even if it's a section of it. But at this particular point, the whole liquid, this one, of which its density, that's what we are calculating, it's not there. So we're not going to choose that as our common height. We'll choose this one as our common height because the liquid will be above it. Now, let's say pressure at, let's say this is region A and this one is region B. So we'll say pressure at A must be equal to pressure at B. Remember, A is the same height from the ground, same as B. So they must have the same pressure. So pressure at A is being pressed by two things, the liquid and the atmosphere. So we'll say HL rho Lg plus pressure of the atmosphere, while B is being pressed by also two things, water and the atmosphere. So we'll say H water, rho water, G plus pressure of the atmosphere. These two must be equal because from here they are equal. So we'll say HL rho Lg plus pressure of the atmosphere is equals to HW rho Wg plus pressure of the atmosphere. Now pressure of the atmosphere will cancel out because when you take this one, this pressure of the atmosphere, the other side, this one will be negative once it reaches the other side, and therefore these two cancels out. And because of that, we'll have the following. We will have HL rho Lg is equals to H water rho water G. So let's key in the values. HL will be 25 all over 100. HL will be 22 all over 100. Remember, we are working with only SI units, but when 2 was in centimeters, so you have to divide by 100 too, so that you can have that length in SI units. Density of L, that's what we are looking for. So just have rho L times 10. 10 is the value for gravity. H water is 25 all over 100, and that is the height for water times the density of water is 1 gram per cubic centimeters, but we need to convert this one to SI units. So 1 gram per cubic centimeters is the same as 1000 kgs per cubic meter. So we'll multiply by 1000, then we multiply by 10. 10 is the value for gravitational acceleration. So we have also common values on both sides. We can cancel them. So we'll first start by cancelling 100 by 100, 10 by 10 on the other end. Then rho of L can be written in terms of the remaining values, that is 25 times 1000. 25 by 1000 divided by these 22. When we divide both sides by 22, we'll have 22 over there. Then we are going to key in the whole of that into the calculator, and this is what we will have as our answer. 1103 1136.36 kgs per cubic meter, and that is the density of liquid L. So state a possible reason why mercury is used. Mercury is used, number one, because it cannot mix with liquid L and water. So it cannot mix, that's why it's used. Then number two, mercury is used because it occupies a smaller height. Remember, it has a very large density. Then number three, mercury is used because it cannot react with the two liquids. Cannot react with water. It can also not react with liquid L, whatever liquid L is.
If you watch this video up to this point, it means that you love the content. Help us spread the word.